In this video, you and I are going to take a look at some controls and techniques that we can use to maintain application security. Let's begin. Back in the 1970s, when I was growing up in California, my dad, at his house, he had this centralized vacuum system. So in the garage, there was a big industrial looking appliance that had the motor and such. And then strategically around the house, they had these receptacles, and you just take the hose and plug in and use that as your vacuum. It's pretty cool. So what I was curious about was, okay, exactly what makes the actual motor that's located in the garage actually turn on and start the suction? And as I recall, back in those days, the one we had, it had two little like ball bearing connectors here that once you pushed in the hose, the metal connector completed the circuit, and that's what turned on the motor. It looks like on this one, however, it might be this little doodad right here. But anyway, I was curious. And so what I would do is I would actually test various things. For example, I thought, I wonder if I push on these two little connectors, if that will go ahead and start the motor. And as I recall, I had a pencil or some other object, and I was trying to push them both out at the same time. And I learned at a young age that it wasn't going to happen based on pressure and based on using a non-conductive material. So eventually I discovered, just by testing various things, that if I put a circuit across those two little connectors, that metal, that conducting material between those two connectors, is what turned the vacuum on. So I could open the flap, make a connection with something metal, and that would turn on the vacuum. And that was all learned based on trial and error. I also learned that various things would make it all the way in and through to the vacuum in the garage. For example, small chunks of hot dog to a certain length would make it all the way through. And if the hot dog was too long, it wouldn't make it through the bends, it would get stuck. I also learned that water in fairly small quantities would make it all the way through without damaging the system. However, I also discovered that if there was too much water, it wouldn't be able to suck it all the way through, and it would start dripping right here out the outlet. And all those things were learned through trial and error. Now you might ask, okay, Keith, that's fun, but what does that got to do with application security controls and techniques? Well, one of the trial and error methods that we're often going to use with applications is a process called fuzzing, or fuzz testing. And it's really a bunch of trial and error. Let's take this server as an example. Let's say the server is running a custom application that we wrote in-house, or maybe it's an application that we purchased. It's a web-based application. And Bob is sitting here wondering, I wonder what would happen if I sent this string over to the server. Or I wonder what would happen if I'm given a web form to go ahead and log in. I wonder what would happen if I put in some script commands, which to the server might be unusual or unexpected input that the server then might process. So what we're doing with fuzzing is we're sending variable inputs, either through URLs or through input screens, and then observing the results of what happens when we send that information in. So what's a really effective way for Bob to actually generate a lot of different random input and send it into an application? Or allow him to test a large set of variables as he sends them into a server, to that application running on the server? The answer is Bob is very likely going to run a fuzz testing application or tool that does it. Backtrack and Kali Linux have several tools built into those distributions of Linux that will actually do fuzzing. Now there's a couple of different camps regarding fuzzing. Now we may do fuzzing, the owners of the application, you and I, because we want to see how our application is going to behave. And that is the operative word. We want to make sure that our application is behaving correctly. If it gets an error, we want to make sure it's doing proper error handling and not going belly up or exposing information. So we're doing the fuzzing to help identify any vulnerabilities in the application. And the attacker may be doing fuzzing to identify new vulnerabilities. For example, maybe there's a vulnerability in an application that has not yet been discovered. So the attacker, by using fuzzing, if he's able to discover some vulnerability, then the attacker can simply document what the unusual input that he sent over to that server, or what script he used, in which box of an input form he used. And then once that's documented, the attacker could go ahead and use that again against this system or another system that's running that application. And until that's discovered by somebody else, that would be an example of a zero-day attack. And let me go over here and write it too. So we may do the fuzzing for discovery, and the attacker, number 2, may do fuzzing to learn about vulnerabilities on a system. Now, what are some of the results that could happen as a result of fuzzing? Well, if our application is solid and we're doing proper input validation, which is the big key here, to making sure that the server is not going to act on any data that's outside of a set of fixed parameters, aka the server is not going to accept a bunch of random strings or scripts that are being fed into it, that would be ideal. However, if we do have an application that is susceptible or has a vulnerability and it's discovered via fuzzing, we might have an application error, we might have the application crash. It's possible we could have a buffer overflow on the system due to the fuzzing that was done against that application. And through fuzzing, if we have a weak application, we might discover that, you know what? When the system is asking us to log into this application, and it's asking for a username and password, through fuzzing, if we found out that an asterisk in the username and an asterisk in the password was acceptable, and the system said, great, you're in, or in the username, if we put in root, and for the password we left blank, and it let us in, that would be a significant problem with the application. So with fuzzing, we can test the reliability of an application accepting things like usernames and passwords correctly. And ideally, if there are issues that are on that application, on that server, we would want to be the ones that find that via fuzzing and using fuzzing tools before an attacker discovers them. And that way we can maintain our confidentiality by making sure that proper usernames and passwords are required to get access into the system. Fuzzing could also help us verify that data integrity is being maintained. Maybe a user who's currently logged in sends a whole bunch of weird data in one of the fields to the server. And in a correctly crafted application, we're going to have valid input verification before we tell the server to go ahead and process that. And by having those validation checks for input, we're maintaining our data integrity. Another benefit is this. If we do fuzzing and we discover that, oh my goodness, this certain string of input, when done a certain way, is going to cause a buffer overflow attack, and as a result cause the application to stop working altogether, we could go ahead and correct that problem within the application, and as a result, that would also improve our availability because the application wouldn't crash and totally stop. Now, there's a great chance, even if we did a lot of fuzzing against the application of the server, there's a great chance that we didn't try every possible random string of text and scripts in our fuzz testing. And so that leaves us open to a possibility that there is some magical combination of script or text that could compromise a system. So how do we protect against that if the attacker is trying a fuzzing attack against our application? And the answer is simple. Inside of our applications, of course, we're going to have code review. And also inside of our applications, we are going to have proper error and exception handling. And the ability to properly handle an error or an exception that the application wasn't expecting by building the routine of what exactly the application should do if there is an exception or an error, that can be used to prevent disclosure of sensitive information by that application in the event the attacker is doing fuzzing against that application. And the key here is this error and exception handling. This isn't something that's done like after the fact. Oh, by the way, now that we have this application running, let's do some error and exception handling. It has to be built in to the code. Here's an example. Let's say we have some software that we've written. So let's say this is the base code. And then we have various modules that interoperate with that base code. And as a whole, we can call this our application. So this is module 1, module 2, module 3, module 4. Just logical software modules that are being called upon for various functionality. When this program is being created, it can be designed to handle a program exception by, for example, restarting a module if the problem was in that software module. So in this example, if module 4 as part of the application crashes, the exception handling could be to go ahead and restart that module in a safe and secure manner. What we want to avoid is any kind of unknown state with the data. We want to make sure there's total control all the way across the board. Now, there's another little dilemma here. If we do have a component of an application that crashes, we need to have some output that indicates what happened. From a programmer's perspective, the programmer wants to know the nitty-gritty details of what happened and why that module crashed. However, the attacker doesn't need to get that level of detail, because the attacker, if he's doing a fuzzing attack and caused a module to crash, the attacker would love to know as much detail as he can about what happened as he documents his fuzzing attack. So the output might be twofold. We might have the output that goes back to the user that simply says something like, an error has occurred. Please try again. Or something fairly generic. Or perhaps, oops, there's a problem. So it may be something simple like this that doesn't give the attacker any kind of significant detail about what really just happened. At the same time, we'd also want to have logs somewhere regarding this application, the detailed information that may say module 4 of application X had an exception at whatever time it was and terminated. Now also, as part of the exception handling, if it's been programmed to restart that module, there should also be another log message that says module 4 of AppX restarted at, and then a timestamp. So all this really cool detail is needed for the developer and for troubleshooting and for correcting that code. While at the same time, the end user should get very little information other than telling them what to go ahead and do. Now that message might say call the help desk or call the administrator. It may not use the word error. It may just say please try again. Because the best practice with exception handling is to log all that detailed information for the benefit of our internal systems people and the app developer, but publicly display for the end users a simple, very generic message. Because we do not want to aid the attacker who's doing fuzzing against our application by giving him tons of detail regarding how successful he is with that fuzzing. Now you may have noticed that input validation as part of a secure coding concept, that idea is not brand new. We've had that in several of our videos in this course. So let's take a moment together and just remind ourselves what are the benefits of having an application where when a user inputs data, whether it's a form of some type or it's a URL that's being sent to the server, let's remember the benefits of having an application validate that information before it's actually processed. Because unfortunately, if we don't validate that user input that's coming into our application and we just execute it, that absolutely could be a huge vulnerability in our application because we're not checking the input. And we don't want to have open and exposed vulnerabilities that hackers can take advantage of. When I was in school, I learned about something called a Ben Franklin balance sheet. And what it would do, it would have the pros on one side and the cons on the other regarding a decision. So if we take a look at input validation, what are the cons? It actually takes more time to program. Because if we have some function that's happening like input validation, the code has to be there and somebody had to create that code. So that would be a con. It takes a little bit more time to do input validation inside of our applications. However, what are the benefits or the pros regarding doing input validation? Well, we can mitigate against a buffer overflow attack by checking the data before it's actually processed by the system. So if there was some input that was going to cause a buffer overflow attack, and we're doing analysis of that input before we process it, we could mitigate a buffer overflow attack. That's a huge benefit. Now, what else could we mitigate by checking our input? Now, from our previous videos, you might be saying, oh, Keith, I know. We could mitigate against a SQL injection attack. Absolutely right on. We could also mitigate against an LDAP injection attack, or an XML injection attack, or cross-site scripting. If somebody's trying to put JavaScript code right there, or other syntax that might try to execute code, either on this server or have this server turn results back to a client who's going to execute script, we're mitigating against that as well. So let's say we have a form that the user is putting data into in an application, and somebody leans on their keyboard, and they just hit the A key a whole bunch, A, like 1,000 times. So they're not a malicious attacker, but at the same time, we don't want to take this huge string of A's and have our system try to process it. So by doing input validation, it's also going to reject bad or malformed input. Now, would that long string of A's cause a real problem against our system? We don't have to worry about it causing a problem, because if we're doing input validation, the system can say, oh my goodness, this is way too many characters. I'm going to go ahead and kick this back. I'm not going to process it. Or this is supposed to be a numeric only field. I'm going to kick it back. I'm not going to try to process it. It's going to protect us against any of that bad or malformed input that might be coming into our application. And these input checks aren't rocket science. Let's say, for example, that we have username here and password here. Let's also imagine that as part of our setup, usernames and passwords have certain length requirements. For example, a password has to be a minimum of 8 characters and a max of 12. So for our input validation, the programmer for this field, the password field, would simply look for, are there at least 8 characters? And are there no more than 12 characters? And they would do that in whatever programming language they were using to write the code. Another thing that we might have had as a requirement for passwords is not allowing certain characters. For example, not allowing the less than or greater than symbols. And that might be a good idea, because if somebody was trying to actually put commands in here to inject scripts that they were hoping the server would run, and they are trying to use the less than and greater than symbols, if as part of our password we're not allowing those characters, our input validation for the password could be looking for specifically those symbols. And if they are there, the system could kick it back and say, sorry, please re-enter password. It's not going to bother trying to process that. It's simply going to tell the user to try again. And that can help mitigate against a cross-site scripting attack, or even something that's accidental, where somebody typed in the wrong characters. Again, we're just protecting against bad or malformed input, protecting our application from actually trying to run and process that input. Or if we had some other field that was supposed to be just numerics, as part of our input validation, the programmer could code in looking for just numerics. So if all the input is numerical, meaning there's no alpha characters, there's no special characters, the programmer could also put restraints in regarding the minimum and maximum lengths allowed for that field. And if it passes the test, meaning it's all numerics, if it's in the range, the application will then go ahead and process that information and move forward. Now, at the same time, if the user who's putting the information in isn't clear on what they were supposed to put there, maybe we have a pop-up message. So if they do put an alpha character there, or they put in too many characters, a little pop-up window comes up for the user that says something like, please put only numbers in. This field supports only numbers, somewhere between 8 and 12 characters. Or whatever message we want to give to the user to prompt them to put in the correct input. Another very interesting attack is a cross-site request forgery. It goes something like this. We have Bob, and let's say that Bob is doing some online transactions at BTC Exchange, whatever his favorite Bitcoin exchange is, and he visits that site regularly. Now, what happens is when he visits that site, he trusts that site because he's using HTTPS, and this site is presenting a digital certificate that Bob trusts because the certificate is signed by a common certificate authority that Bob knows about. So Bob knows he's connecting to the right site, and the BTC Exchange is going to know that Bob is really who he says he is because Bob has authenticated with BTC Exchange, usually through a username, password, and perhaps using some additional one-time password mechanism, like Google Authenticator or something like that. So once Bob is connected and logged in, anything coming from Bob's machine, the BTC Exchange is going to accept as coming from Bob. Well, what happens if Lois, and maybe she sends an instant messenger message or an email, it doesn't really matter, and in that email she says something like, check out BTC right now, like something urgent is happening. And then following that, she'll have some syntax that will give him an icon that he can click on, as well as maybe an action. And so if the contents take him to the BTC Exchange, and additionally, if the code is there to transfer 10 BTC to some address, and that's all inside this code that she's attached with this message, either an email, or it could be on a forum, or it could be instant messenger. If Bob clicks on this, and it takes him to that bank and it tries to execute this code, which would be transferring his Bitcoin, that's an example of a cross-site request forgery. Bob already has a trusted connection to the BTC Exchange. The BTC Exchange trusts Bob. Bob is now basically by one click executing a transfer. And the same concept might apply to banking or purchasing something from an online store. And the payload of this are all the instructions for that final destination, in this case the BTC Exchange, to perform some action. And the BTC Exchange thinks, oh, it's Bob asking me to do this. So how do we protect against that? Well, of course, as always, we want to do input validation for anything that's coming in to our application at our site. In addition, to prevent this, the BTC Exchange could require a token, for example, a private session token for all the submissions. So if Bob did click on this because it doesn't include the token for his session, it wouldn't be accepted. Another thing we could do in our application at the BTC Exchange would be to require additional authentication for any specific transaction. So Bob is logged in, yes, he's authenticated, yes. But if he wants to move Bitcoin or purchase a product or do something else, it's going to additionally prompt him again to re-authenticate for that transaction. And that would also prevent the cross-site request forgery that was built into this link that Lois sent that would prevent it from executing. Because Bob would be prompted to authenticate for that transaction, and Bob would say, what? Wait, I didn't do that. I didn't want to do this. And he would stop it right there. There's a story about a man who built a house on a sandy foundation. So he built his house there, and then when the rains came down, because the foundation wasn't solid, the house was destroyed. Well, the same is true in the concept of application hardening. we want to make sure that if we have an application running on this server, the first thing we want to verify is that the operating system is hardened. And we had a previous video on hardening operating systems, doing things like removing default accounts that are not being used, disabling services that aren't going to be used, as well as changing passwords from the defaults so that any unauthorized people who are trying to log on to the system will have a more difficult time compared to just looking up what the default password is for that system. So a good first step to having an application that is hardened is to make sure it's on a solid foundation, meaning the system and the operating system have been hardened. Secondly, when applications are being developed, a lot of times programmers will put in backdoors and debugging that they need while they're building the application. And during development, those may be absolutely fine up to a point. For example, the developer may need to jump into the application immediately and not have to go through the entire login process to verify some change or variable that he's setting. And the debugging tools are going to feed information back to the developer that he needs to help troubleshoot or optimize and work through the code that's part of the application. Now the trick is, before this application actually is put into production on a production server and open to the wild, we want to make sure that any of those back doors, if they did exist, they are completely shut down. Any additional hooks that may have been there just for debugging, which could possibly be a vulnerability to a production system, we want to make sure those don't have a negative security impact on that system as well. And then in a previous nugget, we talked about code review, or maybe a peer code review, going over each line of code to verify that we're following best practices for the development of that software. And then when we do deploy the software, whether it's software we wrote on our own or we purchased it from a third party, there's going to be some basic configuration elements that we're going to want to set up in that application. And part of having a baseline specifying what should be done with this application as it's being deployed, it's a good thing to have, because if we're rolling this out to 15 or 20 servers, we can compare the rollout of each and every one of those against the configuration baseline just to make sure that we've gone through our checklist and that we've implemented the correct security components for the deployment of that software. So our next challenge is this. Let's say we do have an application, it's been rolled out, we've used our configuration baseline, we've done our code review, it's in production, life is great, and then we need to change that software. Maybe we're adding on a module to that software, or we're changing some functionality, or we need to apply some type of an update. There should be proper change control regarding every step that needs to be done regarding implementing that new update. And this goes all the way back to separation of duties. For example, the person who's applying the patch should not be the same person who wrote that patch. And there needs to be checks in place just to validate that this new add-on isn't compromising our security of the application. Because it only takes one vulnerability to ruin the entire application from a security perspective. So like having a big boat, I think that's a sail. So with a boat, how many holes does it take to sink a boat? Well, really it just takes one good hole. And then when the water starts coming in, that's going to be enough to sink it. So any updates we do or patches we do, we want to do them with great care, making sure we're not compromising security as we implement those updates, patches, or fixes. For several decades, the primary database that we've used is called a SQL database, a structured query language database. And a SQL database is a relational database made up of lots of tables, and there's relations between these tables. And there's primary keys and foreign keys, and we use SQL languages to go ahead and communicate with these databases to make requests. Well, over the last decade, some additional types of database has becoming more and more popular, and they're referred to as NoSQL databases. For example, a NoSQL database could be a document database, or a graph store, or key value stores, or wide column stores. So why the change? Why move from this relational database of SQL to a NoSQL database type? And one of the key reasons is performance and scalability. And probably the biggest driver that caused the NoSQL databases to become more popular were a couple companies that we've heard about, like Google and Amazon. And they've just got so much data to pour through, they created new platforms to manage their data. Google created something called Bigtable, and Amazon created something called Dynamo. And these databases were designed to run across thousands of servers. And as other companies that also need to manage large amounts of data wanted to follow suit of Google and Amazon, that was really the birth of NoSQL databases. And one of the telltale signs is that these are designed, just like Google and Amazon's implementations, to run across literally thousands of servers. So if we look behind the covers of most of these large companies like Google, Amazon, Facebook, Twitter, and so forth, it's very likely we're going to find NoSQL databases because they need the scalability and the performance for their businesses. Now, from a security perspective, we don't have to worry about SQL injection if we're using a NoSQL database. So from an application security perspective, whether it's SQL databases or NoSQL databases, the actual software that's being written to make those calls and access that data needs to follow best practices to securely retrieve and manage that data for authorized users. So we've addressed the importance of doing input validation, but the question is, where should we do it? Well, certainly we want to do it at the server. So on the server itself, it's doing input validation. So if there's a form and part of that form is an email address, if Bob, the user right here, types in Bob and submits that, the input validation at the server can say, wait a second, there's no @ symbol, there's no domain name, this is not a valid email address, try again. Now the cool thing is, we can do that input validation on the client side as well. So for example, if Bob is connected to that server, we can have the client side, so code running at the client, actually doing the input validation. And one of the benefits is we have faster responses back to Bob. For example, we have several fields. So here's our email field, here's our first name, last name. So these are fields that he's filling out. So he types in Bob and last name Barker, or whatever his last name really is. And then for the email, if he types in Bob and then hits tab, client-side input validation could tell him right there, oops, warning, this doesn't look like a valid email address. And we could do that before the user ever pressed submit or pressed enter. Now the reality is we could do that type of validation at the server, which would be server-side validation of input, or at the client, which would be client-side validation, or we could do both, which would be an example of doing defense in depth, multiple layers of security, doing that input validation. So if for some reason the code at the client or the server failed to do input validation, as long as one of them was doing it correctly, we could help identify and stop either incorrect or malicious data, including scripts, from being submitted that could potentially harm our system. And that malicious content could be entered as part of fuzzing, or it could be part of a known attack against the system. I've had a lot of fun in this video, and I'm glad that you joined me for it. I hope this has been informative for you, and I'd like to thank you for viewing.